All right, looks like we're good to go. So, welcome everybody. Thank you for coming to the session. My name is Adrian Colyer. I am a venture partner with a venture capital firm called Accel, based out of London. So, a lot of my job is helping to find and build great technology companies. Prior to that, I did a bunch of other things, which if you're really interested, you can look up on Google and hunt down. I also do something else, which is I read quite a lot of papers, and I write about them on a blog called The Morning Paper. And actually quite a bit of what I want to talk about today is drawn from that. So I actually publish one paper write-up every weekday, and somewhat to my own astonishment, now approaching nearly sort of 350 papers that I've churned through as a process of doing this. I write about a broad range of topics in the field of computer science, but with a bias towards distributed systems and database systems. That's kind of a little bit of my bent. I like to take on a mix of kind of foundational papers and also some things showing us where some of the frontiers are and where things might be going. Every now and then I'll do a summary post where I see sort of a major theme coming together, and today's talk is really drawn out of a couple of those posts. And so as I go through, I'm going to touch on a lot of research and other projects. If you want to go and dig up the references and look at some of the papers, you'll find them all on the blog, and the posts are called Out of the Fire Swamp, from which the title of this talk comes, and another post called All Change Please. Out of the Fire Swamp, that name came in reference to a famous paper many of you may have heard of called Out of the Tar Pit from Moseley and Marks, which was a little bit of a rant about sort of how difficult software development is and couldn't it be better, and sort of accidental complexity and things like that. The first part of today's talk is in the same way as a little bit of a rant about how difficult getting data systems right is at the moment, and what could we do better. And so today's talk is really in three parts. In the first part, I want to question your integrity. Not your personal integrity, but the integrity of your data. Have a little look at sort of some of the things that might weaken that, some ways that inconsistencies can creep into your data systems, some that you may be aware of, some that you may not be aware of, and the trade-offs involved in doing that. Secondly, I want to talk about the art of the possible. So once we've had a little look at some of the theory, sort of what could we do with today's systems? What are the compromises that are necessary, that we have to accept? And what are the ones that may be quirks of particular implementations? How should we think about that? What could we do if we'd really pushed on that kind of frontier? The third part of the talk, I want to change tack a little bit, and for those of you who are just in Martin's talk, you're going to get another dose of kind of milliseconds and nanoseconds, etc. I want to talk a little bit about some of the really, really interesting and impactful changes that are coming through in the next generations of hardware that are going to be hitting our data centers, what that means in terms of the distributed and data systems that we might build, and in particular how the changes in hardware affect some of the design trade-offs that we've made really over the last several decades, and what could be possible in the near future. So that's roughly the plan. So let's start off by questioning your integrity. And so let's begin by talking about sort of classic database systems, Oracle database, relational database world, etc. We won't worry about distribution for the moment. And the gold standard in this world is something called serializability. I'm sure many of you have come across that. And it basically says this. Imagine that we've got a number of transactions. Each transaction can involve multiple operations across multiple different objects. And we're serializable if we could sort of take a timeline and lay each transaction out on that timeline so they happen one after the other. And if it's possible to do this for what we call some history, some schedule, then clearly one of the things you can see is that there's no way anything going on inside T1 before it's completed can impact T2, can impact T3. They're fully, by definition, isolated from each other while they're ongoing. That's the gold standard. We very, very rarely hit the gold standard in practice. Why don't we hit the gold standard? Because doing this requires a lot of coordination, which is expensive, which slows us down. And so what we really want to do is not, to do this, we might, for example, have a single thread servicing requests one after the other, processing transactions. That would give you this, but it's not very efficient. We want to run these concurrently. And when we run them concurrently, they may overlap with each other, and therefore they might not be as fully isolated as we would like. And so we can weaken what we call the isolation level. And if you do that, you get into a pretty interesting sort of world. We can catalog, as you sort of dial down the amount of isolation, the different what we call phenomena, or also called anomalies, or also known as ways your data become corrupted or inconsistent, that might happen when you dial back the isolation level. And going back, this is actually from a 1995 paper, I think, a critique of the ANSI SQL isolation levels by Berenson et al. You can see people have categorized and named these things. And so, you know, at the very core are anomalies caused by dirty writes and dirty reads. So if I'm reading uncommitted information from other transactions that maybe gets rolled back to them as never the true value. And you know, without going into the nitty-gritty details of it, you can see that on the right-hand side there's a whole hierarchy of these isolation levels. And yesterday's post on my blog takes you through this in excruciating detail. And as we get stronger and stronger isolation, we prohibit more and more of these various anomalies. What's interesting is if you take Oracle, for example, the default isolation level, something called read committed, most people never change that. That saves you from the top two anomalies, but not from all the rest. So there are various ways, depending on what you're doing, that your application might see spurious effects. The strongest isolation level that Oracle offers is what they call serializable, but what academics actually call snapshot isolation, and the true serializable they view as a step beyond. At that level, you'll see just here, there's still something called write skew that even at the strongest isolation level in Oracle, you're not protected from. The question might be, does all that matter? Will these anomalies actually happen in your application? Do you know or not? And really, I guess what you should do is you should look at all the transactions inside your application. You should analyze your workload. You should figure out at the isolation level you've chosen what possible anomalies could happen given that workload and whether that matters to you or not. You know, maybe this impacts some constraints you care about. Maybe it doesn't. That's what we should do. I've never, ever, ever yet met a single development team that's done that in the wild. So instead what we do is, because these things are really hard to get your head around actually, so what we all do is we ignore it and we pretend that these anomalies don't happen. That's pretty much the status quo. Another reason this is really hard is that, remember, the problems occur when we overlap the transactions, we run them concurrently. So you can look at each transaction one by one in isolation and they're all fine. That's kind of the point of them. It's the interleavings that make it hard. And so you might have something you've analyzed that's perfectly good, and then you come and add one more transaction in the mix, and you could be exposed. There could be a consistency problem. Or you could just change an existing transaction. So this is really tough. People don't do it. Since it's the one that Oracle Serializable doesn't protect against, I'll give you an example of one of these more extreme anomalies. This is something called write skew. It happens when we've got constraints across several data items. So in this case, I've got a little data store. Imagine it's got an X and a Y, and we have an invariant saying we want to be true, that X plus Y is always less than or equal to 100 for the sake of argument. And so you can see here, first transaction comes in, that's T1 on the top, it reads X, it's 30, great. I'm going to set Y to be 60 because 30 plus 60 is less than 100, all is good. The problem is that interleave with that, T2 has come in, it reads Y at 10, so it's great, I'm going to set X to be 50, 10 plus 50 is less than 100, all is good. When you interleave these things, even though they've obeyed all the other rules, we end up with actually blowing our constraint because the two things have interleaved. Don't worry about the details, it's just an example of the kind of subtleties that can happen. You may or may not have that kind of constraint in your data, but there are things to be aware of. So you may be wondering, well, is this all sort of very theoretical and academic? Do these problems happen in the real world? People are worried about that as well. And so wonderful work by Alan Facchetti. I actually wish I knew how to pronounce his name. I'm going to go with Facchetti, it might be Facchette, quantifying isolation anomalies that actually looked at exactly this problem. How can we figure out how many of these anomalies we're likely to see in our data? And they built models that went and looked at this and tried to get some answers. And obviously there's a lot of factors that predict whether you're going to see violations in this kind of way, but they found, depending on the workload mix, the isolation level, the number of concurrent clients, and other things you can imagine impact this, between about 0.5 and 5% of all their sort of transactions saw some kind of anomaly. And all of that assumes that you're actually using the database to do what it was designed to do in the first place. There's a much more recent paper that is a wonderful read. If I think academic papers could be dry, you should read this one. It's just fantastic. It's dripping with great quotes. And it's called Feral Currency Control, and it's by Peter Bayliss et al. And they basically said, you know what's been happening is more and more and more people are using these things called ORMs. We as a database community, what are these ORM things and what do they do and why are these application developers not using the database properly? And so they said, well, actually they're trying to enforce all kinds of invariants with the annotations and validations and other things. They pick on the Rails validations framework, and as a Java programmer, you read it and you feel quite smug, like this could never happen in Java with JPA, and then you get to the end of the paper and you go, oh, it does. So the examples are Rails, but we're not immune in other places. They said, what are these feral concurrency control mechanisms that people are actually using? And there's a great quote, I'll just read it to you briefly. By shunning decades of work on native database concurrency control solutions, Rails has developed a set of primitives for handling application integrity in the application tier, building from the underlying database's systems perspective a feral concurrency control system. And so the databases might be pretty good but not perfect, but we don't use them to their fullest extent. And so these guys looked at Rails and the validations, and they analyzed a whole ton of open source projects and other things they could get their hands on to see which validations, if you're in Java, think annotations, are most frequently used. And that's the table on the left. And then they asked, well, hang on a minute, which of these are actually safe? Which do what they say they're going to do? And that's the curious column that says iConfluent. In this way, basically, just think of this for the time being as, do these work? When I say, for example, this must be unique, is it going to be unique or not? And they theorized that particularly with things like uniqueness and associations, etc., that these validations don't do what they say they should do. When you really analyze it, and that's what the graphs on the right are showing you, for example, the blue line at the top is, imagine for a minute I didn't have any protection at all, and I just run this test. How many duplicate records would I get? And you see that's about 10 to the 4. And then they run the Rails app with the validation in place saying this should be unique, and they ramp up the concurrency, and they say, well, how many violations do I get? And I guess the key thing to notice is the answer is not 0, and actually as you ramp it up, it starts to approach the blue line. So, as I say, the preceding experiments demonstrate that indeed active record is unsafe as deployed by default. Validations are susceptible to data corruption due to sensitivity to work isolation anomalies and many other things. And so we're in kind of this state of the practice. Actually, it's not really a terribly great place at the moment. But of course, we've got to introduce another factor. We've had the whole NoSQL movement, the drive for scalability at all costs, and availability and other things cloudy. And so we started to build distributed data stores. And so now I've got to layer in a distributed facet on top of this. And the gold standard coming from a distributed systems perspective is something called Linearize Ability. And now we're talking about, for the moment, single operations on single objects. And what I want to be able to do is draw a timeline and say each operation I should be able to place at one distinct point on that timeline. Now you may be wondering, why on earth would I never, what on earth would have stopped me from being able to put an operation at one place on a timeline? And the answer is, of course, that many of these systems have multiple nodes. And so imagine, on one node, an operation happens and starts to propagate to the others. On a different node, another operation happens and starts to propagate to the others. Do we all see the same overall ordering or not? If it's linearizable, we do. In many systems, we don't. And so for the gold standard, each one of these would march forward in lockstep. Again, as you can intuit, this takes a lot of coordination. And so it's expensive and slow and actually hard to achieve if you want some things like full availability. So like with strict serializability, we don't always do it. And instead of weakening the isolation level, which was all about the concurrency, we weaken what we call the consistency. How consistent are the views across these nodes? I'm sure you've come across this idea. When we do that, there's a whole new set of anomalies that can happen that get in the way of our data and applications. Things like, for example, nonmonotonic reads. This is where I read some version of a particular data variable, and I read it again later, and I now see an earlier version of it. That can really confuse you if you're not expecting that kind of thing to happen. And there are similar things for non-monotonic rights, and there are issues for example, if I see the effects of some transaction and then I go commit a second transaction, anybody seeing the effects of my second transaction should also be able to see the first, otherwise they might be wondering what the hell I'm doing, etc. Read your rights is a fun one, which says if I write a value and I later read it, it would kind of be intuitive if I saw the value I'd written or one that superseded it, but that's not guaranteed. And so you get these guarantees that I've put on the right-hand side, and you can start to combine them. And so if I have a promise of have monotonic reads, monotonic writes, writes follow reads, I get something that the academics call pipelined random access memory. If I add read your writes to that, where I want to get to, you get something called causal consistency. That's going to be important in a minute, so remember that idea. Let's take a look at where one of these things can go wrong, just as an example. So here's a non-monotonic read. Got 3 replicas, x1, x2, x3. Starting off on the left, they're all consistent, they're all at value 0. First session comes in, writes x is 10 and commits. It's gone into just to the first replica in this case. Second session comes in, reads x is 10, it's got version 1 of this value. Meanwhile, in the background, that value starts replicating from x1 to x2. But session 2 comes in and reads it again, this time from replica 3, right before this value is propagated to it. Now it sees the 0, it's gone back in time in a version, and all sorts of curious things can happen if your application isn't coded to be aware that these kind of things can happen. And so, there's a great paper called COPS, Clusters of Order Preserving Systems, that describes what they call the Alps Properties, which is what we're all after when we go for these big systems: availability, low latency, partition tolerance, and scalability. And in pursuit of those, if you've heard things like the CAP theorem, etc., particularly saying we've got to be partition tolerant because partitions happen, and it's true, we're going to have to do a bunch of things and accept all these trade-offs, particularly weaker consistency, etc. The interesting reality is that when we made all those trade-offs, if you've read the Jepson reports by Afir or Carl Kingsbury, if you haven't, I strongly recommend you go take a look. Basically, they show that in the real world, these partition tolerant systems really aren't. And when you get partitions and they heal, you get all sorts of data loss and corruption and other systems in the real world. So it's possible we've slightly thrown the baby out of the bathwater. How often do these kind of consistency anomalies happen? Well, there's another great piece of research, again by Peter Bayliss and team, called Probabilistically Bounded Staleness. They've even got an online website where you can go and play with it. And so you'll find this, if you Google that, you'll easily find the tool. Go to my blog, you'll find the link. You can put in how many replicas, how many do I need to contact for reading, how many for writing, what's my latency for various requests. Here I've got this tuned to the Cassandra default, and I've picked about half a millisecond latency. That's probably a bit high, but just to give you an idea, to make the chart interesting. And you can actually work out probabilistically what's the chances that I'm going to see one of these anomalies or not. And you can play with this tool, which is kind of quite fun. Now, so far, we've just been talking about linearizability of single operations, but what about if I actually want to do transactions across multiple entities in this distributed setting with my distributed data store? Well, if we put those two together, we add linearizability and serializability. The gold standard would be something that looks like this, which we would call strict serializability, which basically, even just forget the strict serializability version, frequently not supported in most of these stores. So you can't do multi-entity transactions. Again, to quote a paper called Scalable Atomic Visibility, in recent years, many NoSQL designs have avoided cross-partition transactions entirely, effectively providing read uncommitted isolation, which, if you go back to a few slides that we started with, means a lot of bad things or interesting things can happen. And so actually Hollywood made a film about this, who knew, which they called The Anomaly. And the basic plot is that the anomaly is out to get you. You've got 9 minutes and 47 seconds to figure out what to do. Good luck. Okay, so that's a brief tour of some of the state and issues, just to get a little background in your mind. I want to leave you with a quote from Google, who are obviously a big cloud company, very experienced in doing things at large scale. It's from their F1 paper, F1, a distributed SQL database that scales. And they said this: look, we've got a lot of experience at Google with building these kind of eventually consistent systems. And what we always find is that developers are spending a hell of a lot of their time building a lot of very complex and very error-prone mechanisms to cope with these anomalies we've been talking about and handle data that may be out of date, etc. We think this is an unacceptable burden to place on developers, and consistency problems should be solved at the database level, and on they go. So the interesting thing is that even at a company like Google that have tried this at length, there are significant groups saying this is a real problem for us. So part 2, what can we actually do? What's possible here? So here's an interesting result. Consistency, availability, and convergence by a group of authors. I always love the fact that the first one is a Prince Mahayan. Don't know him, but I love the name. And they proved something really interesting. They said, look, no consistency stronger than something called real-time causal consistency. Remember, we saw that causal consistency thing before. Can be provided in an always available, the always is important, one-way convergent, that means people eventually agree on what the data value should be, system. So you can't do better than that, but also you can provide this level of guarantee in an always available one-way convergent system. So to me, that sets a baseline saying, look, I should be able to get at least this guarantee. And there are a bunch of practicalities in it, but that's what I'd really be looking for, because all that development pain, etc., of dealing with the anomalies is a problem. So we know we can get causal consistency. What can't we protect against in that world? Another great paper, Highly Available Transactions, Virtues and Limitations, that says if we want sort of high availability or always on availability, which has a precise definition, by the way, it means if I can contact any one node, I can continue to make progress. So it's not like if I'm in the majority partition, for example, but any one node, what can you do? Turns out you can't protect against 3 of those anomalies we saw right up the front: cursor locked updates, lost updates, and write skew. We can't protect against something called stale read, so we can't give a recency guarantee on how recent a data item you read can be, and we actually can't do the read your writes thing that we looked at. Although we can do that, tying back to the previous slides, if we make sessions sticky. So if a client always goes back to the same node during the session, we can give you that guarantee. So this is kind of an idea of where the bar could be, theoretically. So what do we do for these things that, assuming we do want these high availability properties, etc., and the partition tolerance and the scalability, what should we do about those things that we can't protect against? Now we go back to some interesting work, very influential by a guy called Pat Helland, who's written a bunch of wonderful papers, really good writing style. He wrote a paper called Building on Quicksand that kind of talks about some of the perils and the shakiness of what's underneath us. And he said, well, really, think of it this way. We've got a basic model is that your system has a memory based on what it's seen, so its current view of the state. Based on that memory, its current view, it makes what we're going to have to describe as its best educated guess as to what the action is that it should take. Accepting that for reasons of weakened consistency, weakened isolation, that guess may actually be wrong. But what we should do is if we find out we made a wrong guess, we should detect it and we should apologize. Otherwise, we should have some kind of compensating action. So you've got this model of memories, guesses, and apologies. One of the great things they do in this paper is they say, actually, you know what? Before we computerized everything, this is how real businesses used to work. You know, it wasn't possible to have real-time knowledge of information across a bunch of disparate offices. So go study all those old paper systems and how these businesses worked. And that gives you some insights as to how to build a memories, guesses, and apologies system. There's another really powerful thing we can do. There's a long-standing benchmark called TPCC that some of you may have come across. It must date from, I would guess, late 90s. I should have looked that up, but it's been around a long time. There's no cheating here. It's a kind of a transaction processing gold standard benchmark in certain places. I remember many EJB systems. Remember EJBs back in the day? Used to show off how they could do this. And there's another great paper called Coordination Avoidance in Database Systems that says, actually, hang on a minute. If we think about the invariance at the application level rather than at the database level, and we analyze the application in a way that I said was really hard to do by hand, but maybe we can do with some help in software, we could understand which of those invariants actually are likely to be violated if we don't coordinate, and which ones don't require coordination at all. And they looked at the TPCC benchmark as it is under those constraints, and they found that there are basically 12 invariants that need to be upheld in that benchmark. 10 of them don't require any coordination, which is somewhat surprising for a classic transaction processing sort of benchmark when you look at it. And so they said, well, let's do this. Let's build a system that only coordinates when it has to. The graphs are on the right, looking at total throughput in number of transactions per second. Those are marked off in millions. And throughput in terms of number of transactions per server. Getting really quite impressive scalability results on the new order benchmark. If you put all the pieces together, you might end up with something that looks a little bit like this. Again, sort of go to the blog for more details on this sketch, but some of the things that we start to know from the theory is, at the top level, specified by our applications or by the user, what are my application level invariants? Obviously, the transactions that we want to run. If we can do that, we can do this, what we call invariant confluence analysis, and find out where the places are that we have to coordinate. When we do need to coordinate, we know that we'd like to do it in a causally consistent manner because that's the strongest we can get, which is going to give us the most protection. Turns out we can actually do that in a bolt-on layer if we wanted to. There's a paper called Bolt-on Causal Consistency that shows that you can build on top of a weaker consistent store, like an eventually consistent Cassandra or something, a layer that gives you the causality. Then the last thing we've got to do is monitor what happens to pick up violations, and then maybe have some kind of callback to let the application take its compensation mechanism. And so we might put these various things together. The last little tweak in the middle, I won't dwell on it for too long, for causality, which often is described as happens before, there are two ways that systems do this. One is what we call implicit causality, which basically says everything that happens on the same thread, maybe on the same node, if it happens before it in time on that node, we assume that it's a cause. The metadata for that can get quite big, as you can imagine. Another variation is explicit causality, where we, the application developers, say, these were the causes of what I just did. Much smaller metadata, much more efficient. Okay, so what happens? What does this look like? Number one, avoid coordination when you can. And again, the research shows that we can do this fancy thing called I-confluence analysis to do that. When we can't avoid coordination, use causal plus consistency. That's the strongest we can get. It's going to give us the least anomalies. Detect, so you actually got to look for it and apologize for what you can't prevent. Little tweak in the middle, there's some great work on things called sort of brownout aware load balancing and brownout systems. If you're familiar with the idea of a circuit breaker in Netflix's world, for example, that basically trips when something goes wrong. I think of these more like dimmer switches. So what happens is you notice that you're under heavy load, and then you start dialing back what you do. Now, you could dial back elements you show on a page or whatever, but you could also say, under light load, why don't I use even stronger consistency when conditions are good, then I can afford to pay for the coordination costs. And under heavy load, I'll dial it back and go back to causal consistency. And what that would do is just reduce the number of anomalies that you're going to detect. The system should be able to hide that from you. A couple of last things in this section. Remember we said that most systems don't provide multi-partition transactions. Turns out that we're starting to chip away at that. So it is possible to provide forms of multi-partition, multi-entity transactions that are actually very valuable things to be able to have. Something called read atomic multi-partition transactions. Read atomic isolation, each transaction gets an atomic snapshot of the state when it starts. There are several versions. The throughput looks good. This was actually used in that TPCC benchmark number that I showed you earlier. So the takeaway is just some of the things you might have been told about not being able to do these multi-partition transactions may not be quite so true anymore. The last thing I want to touch on in the art of the possible, just because I think it's really interesting, you can take this causal consistency idea and you can also put sort of transactional wrappings around that, which is something that the Swift Cloud project did. And what I really like about their work is they said we can do these transactions, but let's take them all the way to the edge. So if you imagine the enormous compute power, etc., that we've all got in our smartphones, etc., they took their work and said we can actually do these transactions right on the edge in a special case where they're what they call mergeable transactions, which basically means that they use mergeable data structures like CRDTs, etc. And in that case, they can do it at high scale and with fault tolerance, etc. So some really, really interesting work in the art of the possible today beyond what most of the current popular incarnations will actually let you have. All right, so now I want to change gears slightly. This is a very whirlwind tour, appreciate that, and talk about some things that are coming that might disrupt everything I've just told you. And I want to talk about some changes that are coming to data centers of the near future. In fact, some of them are already in data centers right now. And one of the things I've found is that when you talk about all these hardware numbers and we think about microseconds and nanoseconds and milliseconds, etc., I don't have that kind of immediate intuition about how long some of these timescales really are relative to each other. And so what I found really helpful is to put them all into some kind of human time frame. And so I want to take you back briefly to the world when computer was a job title. And it actually used to be human computers, qualified on that before. That's why we first called that digital computers, because that distinguishes them from the people. So there were human computers who would do computing, sat at desks working away. This is a group who happened to be inside a NASA center doing computing. Okay. So now, this is the world that most of our database systems, etc., were designed for. So I say, here's my computer, remember my human, sat at a desk working away. Could have a paper directly in front of them, easy, data in the register. Could have various piles of different sizes on the desk in front of them, data in the caches. And let's say roughly they're pretty good, they can find any paper on their desk on average in about 10 seconds. Rough ballpark. That would equate to, in my scale, about the 10 nanoseconds it's going to take blended to do a read from the register L1, L3 cache, right? Now let's add on to that. Suppose the computer doesn't have the file on their desk. That's fine, we're in an office, several computers in there. We have filing cabinets, great. We'll go over to the filing cabinet, we'll look for the file we need, and we'll get it out, bring it back to our desk, and we'll start working on it. Computers are pretty efficient at that. They can get across the office and grab something out the filing cabinet in about 1 minute and 10 seconds, something like that, which is pretty good actually. If you remember working in a time with real filing cabinets like that, which I just about do for my sins, that equates to reading from main memory, about 70 nanoseconds or so. You could argue the tens of nanoseconds, but the ballparks are right. What happens if you have to go to the warehouse? So we haven't got the file in the office, it's not in the filing cabinet, it's not on anyone's desk, it's in the warehouse. Or maybe we've got some clients who believe that the office is a fire risk and they don't trust the information that we have until we've securely deposited it in a warehouse and we've got back an acknowledgement from the warehouse manager that this file has been received. So that takes about 10 milliseconds. How long is that for our human computers? Hazard a guess?
About 7 months.
Not far off. Yeah, I think I've done this calculation about 20 times thinking I must be wrong. I've got to check it. It's about 116 days. It's a ton of time to go to the warehouse and deposit this stuff. And actually we only have fairly small trucks that go. So you can imagine now you're managing this team of computers, the people doing work, thinking about how are we going to do work, given that these are the times it takes to do things. And all the hoops you jump through to be really damn efficient every time you had to go to the warehouse and back. That's how we designed most of the current generation of data systems for this world. Okay, so a bunch of stuff is happening that's really interesting that I've only really got time to flag up quickly. Maybe starting top right, since Martin touched on it, super fast networking coming in the data centers, 100 gigabit Ethernet, something called RDMA, which is remote direct memory access, that did come in a while back with InfiniBand, but now is being rebirthed on top of Ethernet, something called Rocky, which is really interesting. You can do these one-sided RDMA reads, amongst other things, that actually let you get data from the remote memory of another computer without touching its CPU at all, just all done in the NIC, which is kind of interesting. There's some really exciting new storage stuff coming in. Two variations, something called NVMe, which is attaching your storage over the PCI Express bus, which is just way faster than it used to be. And there's a whole new generation of non-volatile memories coming through. Touch on that in a minute. In memory itself, we're figuring out how to do things like what I call the lots of little batteries strategy, which is to take our DIMMs and make them non-volatile. You put a little battery or just enough of a capacitor so that if you lose power, it knows I can just take the data that's in my memory and move it safely to an SSD or something. Just enough power to do that, which lets you treat the memory like it's persistent. There's also a next generation of genuinely persistent memory coming through. Changes a bunch of things. In computing, there's a bunch of other interesting things like HTM we've had for a while, but if the memory is persistent, as we'll touch on, then that blend gets interesting. There are new instructions coming through in the works to make dealing with this persistent memory more efficient. There are things like onboard FPGAs. It's actually also coming as an Amazon instance type in the next few months, unbelievably. A tremendous rise in GPUs that's been massively exploited by the machine learning cycle, for example. A ton of interesting stuff happening. One of Intel's sort of big things they talk about is called 3D crosspoint, an example of this new generation of memory. You see it sort of sits somewhere between classic DRAM and your NAND flash, but closer towards the DRAM end of the spectrum. You can use this in kind of two ways, like it's a slightly higher capacity persistent but slightly slower memory, or also like it's a really, really fast SSD, very briefly. And here's another look about when you do that really fast SSD thing and you attach it via this NVMe or PCI Express bus, then if the basic NAND flash was about 100 times lower latency than a hard disk, this guy is about another 10x reduced versus the NAND flash. So it's really interesting. What does that do to our human computers? What new options do we have? And so, first of all, now we've got some new filing cabinets, super duper filing cabinets in our office. They're about 4 times the capacity that we had before, and they're fireproof, which means that clients might be happy that we don't have to go to the warehouse anymore. We've got protection around it. Things are persistent in these filing cabinets. We can get to those in about 2 to 10 minutes. Another thing Martin touched on, amazingly, with this RDMA, it might actually be much more efficient to phone another office, get them to fax over the data, i.e. go over the network to another computer and get data that's there. We can do that in 23 minutes odd for a one-sided RDMA, 40 minutes-ish if we need to do an RPC. That's equating to about 2.4 microseconds, by the way. Much faster than we can go to a disk that's locally attached to our own computer. Even though, actually, these next generation warehouses are pretty darn special. We've got huge, I don't even we call them trucks, I don't know what we call them, something really great going to these. We can round trip in about 3 hours and 20 minutes now. So that's roughly what's happening with the new hardware on a human scale. What you can imagine is, now take a world where these things are true, how would you design the system, what trade-offs would you make? They're awfully different potentially from what you did before. And so here's a bunch of new numbers everybody should know. They're on the blog. I'm not going to dwell on them. Also on the blog, you'll find all the sources I drew these from. One of the things I'll say is, the more sources you look at, the harder it is to figure out what the true answer is. But approximately they're right. So, the last little piece. What are people doing who are starting to look at what could be possible in this new world? So there's a great project out of Stanford called RAM Cloud that's basically said, let's connect a whole bunch of servers, say 1,000, together, keep the data in memory, let's have like a few petabytes, and we'll use this fancy RDMA networking thing to connect them all up and build a system. And they can do reads in about 5 microseconds, writes in about 13.5 microseconds. So RAM Cloud is tuned for each of the systems pushes on one dimension. How low latency could we get? Pretty darn low latency. They added on top of this something called Rifle, the reusable infrastructure for linearize ability. Here's a paper, and using that they were able to do transactions and multi-entity transactions and other things, again in a few tens of microseconds. Pretty darn quick. Okay, let's keep going. Pretty darn quick. I can't see you as well, but you can still see this. Their TPCC benchmark, though, the trade-off for ultra-low latency is not such good throughput, so about 33 transactions per second. That's exploiting RDMA. Remember I said, we were all taught to believe that we couldn't do multi-entity, multi-partition transactions. That was a great paper, again, from Pat Helland, Life Beyond Distributed Transactions. Another great paper recently is called No Compromises, Distributed Transactions with Consistency, Availability, and Performance. And they've got some really great numbers out here. So they're using the combination of RDMA and lots of little batteries techniques to make their memory persistent. And on TPCC, they got 4.5 million transactions per second, albeit across a 90-node cluster, and about 1.9 milliseconds of latency, which is really slow compared to RAM Cloud, but still pretty darn good. Or in a key value store that wasn't transactioning the same way, some really, really great numbers. Again, what I really want to take away from this, the summary, this paper demonstrates that new software in modern data centers can eliminate the need to compromise. Farm provides distributed ACID transactions with strict serializability, that's linearize ability and serializability put together, high availability, high throughput, and low latency. How did they do it? They leveraged the new networking and the inexpensive approach to non-volatile, that's persistent DRAM. So pretty interesting stuff. Now what happens if we take persistent memory and some of this RDMA stuff and we add in something like HTM and we exploit the hardware transactional management, which when the memory is persistent is kind of interesting. What can you do? Well, a system called Dr. TM pushed on this part of the envelope and they said, well, you know what, we can do about 5.5 million transactions per second on the TPC benchmark on just a 6-node cluster. Now again, you know, they're optimizing for a certain thing, but that's a staggeringly good number with a very small cluster. To give you a feeling for how good that is, I looked up on the TPC site what the current best reported benchmark is for TPCC. Vendors stopped posting numbers, it seems, sometime around 2013. So the record is 2013 for officially verified. It's held by Oracle. They did it with 128 cores, and they did about 8.5 million transactions per minute, which works out about 142,000 transactions per second. So to give you some idea of the scale of change, remembering this is strictly serializable, high availability, and all the rest of it. Really, really interesting where some of this stuff is going. Last thing I really want to touch about is, as I said, when you make these radical changes in the hardware, what's really interesting, everything sort of improved at the same relative rates. The trade-offs we've made in our designs would still be correct, and things would just get faster. But when things improve at very disproportionate rates, some of the trade-offs that we used to make one way are now different. We have to make them another way. And that's what we're starting to see in this. And the paper that really helped me get some good insights into that is this one on the left, From Aries to Mars. Aries, for those of you who don't know, is a very sort of important historical system, particularly for its work around recovery protocols, etc. And in this paper on the left, they said, Mars is a modified Aries redesigned for SSDs using this new NVM stuff. Makes a nice, cute title. They go and say, let's look back at all those design trade-offs that were made and reevaluate them for the new world. And by golly, a whole bunch of things change. It's really interesting. Second paper that I really like is, yes, some things change, but actually also a lot of what we've learned about the issues still remain. One I really love on the right-hand side, it's called blurred persistence, and it's like one of those dull moments. So memory is now persistent. Great. So over the years, we've learned that a really important thing is the boundary between volatile storage and stable storage. So in other words, what we used to say was memory and disk, right? And so, you know, we're safe, our data is durable once we've got it out of the volatile memory and we've put it on disk. When I've got persistent memory and I'm doing transactions, where now is the volatile stable storage boundary? It's actually between the cache on the chip and the memory. And so now we've got to think about carefully managing data that might be in the cache and getting that into our persistent memory before we can say that, you know, it's durable and we're safe, etc. And it turns out actually in a modern processor, those caches are pretty big, like 45 megabytes or so for L3, which is a lot of data. Certainly your transaction data probably fits within that comfortably. And so this paper on the right says, well, actually, you know what? We had quite fine-grained control of how we move things from memory to disk, but much more blunt instruments for getting stuff out of the cache. The hardware hasn't exposed it. And then look at what you can do. In the next generation of chips, Intel are adding new instructions to make this even more fine-grained. So, most of this research stuff I've touched on just combine one or two of these advances. What happens if you put together the really fast networking with ample persistent memory, with hardware transactions, with those advanced instructions I talked about with the super fast storage? Didn't even touch on the onboard FPGAs and the GPUs and stuff. Very, very interesting, very disruptive stuff. The systems we've had to date are not going to be optimal for this new world. It'll be very exciting. Take a while to come through. So that's our whirlwind tour. We started off by questioning your integrity and looked at the various anomalies and the compromises we've made and some problems that can occur. Then I touched briefly on the art of the possible. Where should we expect with today's kind of systems the boundary to be? What should we be pushing for? Then we talked very briefly about some of the really exciting stuff that's coming down the line and what could be possible and appropriate for the data centers we're heading towards. I hope that as a result of that, one of the side effects is I've inspired you to go read more papers. It's just a wonderful world in there when you start looking. One way you can do that, I publish a write-up every weekday, so if you don't want to read the papers, you can read my summaries. They're on the blog. You can get that via email subscription if you prefer. I also announce on Twitter every day, I'm at Adrian Colyer, what the paper of the day is. Go to a Papers We Love meetup. They're great. You get people sort of sharing and talking. Share what you learn. Lots of fun things you could do there. With that, I think about 1 minute before time, I'm going to wrap. That was a super fast whirlwind tour. I say all of the details, all the papers I've referenced and everything are on the blog. A lot of the details about the anomalies, actually yesterday's post, today's post, tomorrow's post. So if some of that piqued your interest, you want to go read more, I encourage you to go there and look. And with that, I will say thank you very much.